Hey, calculus students. This is video 6, where we get to talk about chain rule, which is actually, I think, one of the more useful rules that we use when we're doing derivatives. It allows you to take things that are very complicated and do the derivative in a pretty slick manner. Okay, so I'm going to tell you what chain rule is, and then I think you'll actually find that when I'm using it and doing it for an example, you'll see how it works a little bit better. It's a little hard, it's a lot of jargon and symbolism, I guess, at the beginning. So here we go. The first way of explaining chain rule is the idea that you have a function within a function. So, for example, if I have y equals f of g of x, so notice I have a function inside of another function. I can do the derivative of that. It is defined technically as the derivative of the outside of the function times the derivative of the inside. And I said that a little funky. I'm going to take the derivative of the outside with the inner function still inside times the derivative of the inside. Again, once I do that in practice, you'll understand what I mean. Okay, so let's see this guy in action. Okay, so I do have a function within a function. My outer function is the square root, and my inner function is my 2x minus 3. So I have two different functions happening at once, and I want to take the derivative. So in general, I can think of this in a couple of ways, and the first way that some people think about it is that they're going to take the derivative of they replace the inner function, if you will, with a u, and then they do the derivative of what's inside, and then they replace the u later. So let me show you that version, then I'll kind of show you how I do it. Okay. So if I were to take the derivative of something like this, you guys know we treat that as to the 1/2 power, and then the derivative would be 1/2 u to the negative 1/2, and then technically that would end up being 1 over 2 root u, right? I think everybody's comfortable with that. Okay. But then, and excuse me, there is one thing we need to add to that. So, and then that's du, which means I've took the derivative with respect to u. Okay. Okay. So then over here, this is u. If I found the derivative of this, that would be du equals 2 dx. Okay. So then if I plug this guy, if I replace this guy with this information, I end up with 1 over 2 root 2x minus 3 times all of that, 2 dx, which gives me 1 over root 2x minus 3 dx, because I took the derivative with respect to x. Okay. So that's one way to go through it, this u substitution. I actually prefer to think of it as that first way that I had labeled it, which is I'm going to take the derivative of the outer function of the value and then multiply by the derivative of what's inside. So here we go. This is what I mean. First, you're going to do the derivative using what we have on the outside. So I'm really going to treat this as 2x minus 3 to the 1/2 power, okay? And I'm going to do the derivative of that operation of taking something to the 1/2. So what would you do if you had a power function? You'd bring the 1/2 out front, and then you'd take it down by a power, right? What you're going to do is leave the function intact, so you don't mess with what's inside. This is like the f prime of g of x part. Then you got to take the derivative of what's inside. So, okay. So now I've done the derivative according to the outside and left the function as is. Then I multiply by the derivative of the stuff inside. What's the derivative of 2x minus 3? Just 2. So my final answer, I can cancel out the 2 and the 1/2, and I've got 1 over, this is a negative power, root 2x minus 3. Technically dx because I did the derivative with respect to x, but if you're going to leave this dy over dx, then you don't need it. So it's your choice. Most of the time we just leave it over here. Let's see a few more, and I think you guys will feel a little bit better. Okay, so this guy, I've got two things happening. I've got the fact that it's being raised to the 50th power, which is happening outside, and then I've got this function happening on the inside. So how are we going to do the derivative? the derivative with respect to x. Well, let's do the outer part first. So the outer part, I'm going to treat it like it was something to the 50th power. What would you do? You'd bring the 50 out front. Everything inside stays the same, and I'd bring this down by 1, 49. Then, because there's a function in here, I need to take the derivative of the inside. The derivative of the inside, I'm just going to do one at a time. X squared is 2x. Negative 2x becomes negative 2, and the derivative of 1 is just 0. So I technically don't need that, but I'm just showing it to you. Okay, so then I have 50 times x squared minus 2x plus 1 to the 49th times 2x minus 2. We'll probably, for the most part, leave it like this. Sometimes we'll factor out anything else we can. So because I can also take a 2 out of all of this, I would put me at 50 times 2, or 100. I'm going to move this guy over here. I've already factored out that 2, and then that. Again, trust me, this is fine, but this is going to be where we're headed. All right, let's take a look at this guy. So for this guy, I can think of, I'd probably rewrite this first. So I'd rewrite this as 3 minus x to the negative 5. And then I've got two things happening, right? I've got the fact that I'm raising it to the negative 5th power, and then I've got this function inside. So I want to take the derivative. I'm going to deal with the power first, bring it out front, leave the inside alone, take it down by a power, and then I have to do times the derivative of what's inside. Now, the derivative of what's inside is actually, that's 0, but this is a negative 1. So I am going to get a negative 1, so that did play a role. Okay, then I'm going to go ahead and multiply the negative 1 and the negative 5. And then technically, this is being raised to the negative, so it's really a power on the bottom. And there you go. Okay. In this guy, this is where it starts to get very helpful. You don't have to do a double angle identity. So we have cos happening, and then we have this function on the inside of 2x. So you're going to deal with the cos first, then you're going to deal with the 2x. So let's go for it. I'm going to use this. Even though it says dy dx, I'm going to change it up just so you can see some different notation. So deal with the outside first. The derivative of cosine, careful, is negative sine. But again, you're only dealing with that first outer function. So the inside stays as is. Then you multiply by the derivative of what's inside. So you're kind of working yourself one at a time. We took care of the cosine. Now we're going inside. The derivative of 2x is 2. No, you cannot put that 2 in here. This is trapped inside the sign, but you can bring that 2 out front. Okay, in this guy, I'm going to deal with this as a product rule and a chain rule. So I've got a product because I'm multiplying two things. And again, according to our product rule is the derivative of the first. So this is going to take some time in its own right. The derivative of this is a chain rule. You've got to the third power, which is the outer function, and then you've got the part that's inside. So, okay, the derivative of this is going to be, I'm going to bring my 3 out front, leave everything as is, take it down by 1, times what the derivative is of the inside, which is just 2. Whew, that's a lot. That's the derivative of the first. Remember, here's the product rule. Product rule says if I take f times g, it's the derivative of f times g plus f times the derivative of g. So that was the derivative. All of this is just the derivative of the first part times g. So times 4 minus x squared plus. Now I'm going to take the derivative. Well, actually, I'll do f. So times the first part, 2x minus 5 to the third, times the derivative of the second. So the derivative of this, here's another chain rule. I've got a power and then a function. So I'm going to bring the 2 out front. So this is times, it's a times 2. Everything inside stays the same. Take it down by a power. That's technically to the first. I don't need to write that, but I will to help. And then I do the derivative of what's inside, which is just negative 1. Okay, let's simplify. So we've got, let's see, I've got a 3 and a 2. So I've got a 6. And then I've got 2x minus 5 squared times 4 minus x squared. Here out front, I've got a 2 and a negative 1, so minus 2. I've got a 2x minus 5 to the third and a 4 minus x. Now, technically this is fine, but in the future, we're going to start factoring out like parts. So I've got 2x minus 5s in each, and I've got a 4 minus x in each. So I'm going to bring those out. So let's see, I can bring out 2 powers from both. So I'm going to bring out 2x minus 5 to the second, and it looks like I have a 4 minus x, but only 1 that I can take out of both. So I'm going to take out the 4 minus x. So what do I have left? If I take out the 2x minus 5 squared completely, and one of those, I get 6 times one of those. Okay? If I take out 2 powers of this from there, I have one of those. Well, first of all, I have the negative 2, but I have one of these guys left because I took out 2 of them, and then I took out that whole 4 minus x, so that part's gone. So this I can actually distribute and simplify, and I need to. So I'm going to distribute that, minus 4x plus 10. Simplify that. I get 34 minus 10x. And then again, the cool thing that I know you don't necessarily see yet, but I do, is that by doing this, this is completely factored. So later, foreshadowing, we're going to be setting this equal to 0 later. And when I set something like this equal to 0 that's already factored, I can just set each little part equal to 0. So again, it's just a little teaser. All right, let's try this guy. I think we've got 2 more to go here. Let's give this guy a try. This one has 3 parts to it, so I'm going to try to help you using different colors. So I think the first thing that would make this a little easier is to rewrite this like that, because then you can see that the power of 3 is the outer operation that's happening. Then you've got the tangent happening, and then you've got the little 4x inside. So this is a triple chain rule. And in fact, chain rule you can just keep doing. And I'll show you what I mean by that. So I'm going to start with the outer function. So if I do the derivative of a power of 3, I bring the 3 out front. Everything inside stays as is. And then I raise it to 1 power less, right? Okay. Then I take the derivative of what's inside. Since the derivative of what's inside is also a chain rule, I just start on the outside. So what's the derivative of tan? Secant squared of the inside. And then times, now I can attack the 4x times 4. So one more time, what did I do? I dealt with the power of 3 first, brought 3 out, rewrote the inside, took it down by a power. Then I attacked the tan. The derivative of tan is sec squared of the angle, and I left the angle alone. Then I did the derivative of what's inside. That's where the chain rule comes. It's like you're taking one little part and you're working on it as a chain. Then I can bring this 4 and this 3 together to be 12. And then this is technically tan squared 4x. You can write it like that. Sec squared 4x. Again, notice this is all a product, which will be helpful if I want to set this equal to 0. That's a derivative. Oh, I guess that's the last one. All right. Good luck with the problem set. There are some tricky ones. This is where knowing your trig from last year is really going to come into play. So you might want to review some of those trig rules.